We want to talk about here a physical manifestation of what we call two-state observable. In the previous lecture, we talked about how we're going to deal with discrete state observables, and we said we talked about flipping a coin. But now let's talk about the physical system we'll actually be dealing with. And we'll primarily concentrate on two, but there are actually several physical systems that can be two-state observables, have two possible outcomes of a measurement. And this one we're going to introduce the concept of spin, and the spin 1/2 case in particular. So a little bit of the history goes back to the pre-quantum mechanics day of around 1922. And again, before quantum mechanics came about, there were various ideas about the atom, but one thing that was known, the atom had discrete energy levels. The Bohr model is an example. And there were other Bohr-Sommerfeld theory, etc. There was ideas about the way the energy levels and the angular momentum states of these atoms worked. Turned out there were some modifications once the full theory came out. However, an idea was how to actually kind of do experimental measurements of this, and a very important one in the history of quantum mechanics was what's called the Stern-Gerlach experiment, 1922, to actually measure angular momentum states. Now, it turned out, as I just mentioned, that due to the adjustments needed, what they thought they were measuring were the angular momentum states of an atom, but it turned out later that they were actually measuring the electron's spin, which is an entirely new concept, quantum mechanical concept. But here we'll just review the experiment, and we will discuss just the introduction, how we're going to represent it in quantum mechanics. Not getting into too much depth here. So it's going to be a relatively scant overview of the Stern-Gerlach experiment. Now, the experiment goes as follows, is that you have an oven, essentially, just a source of silver atoms. Now, when you say why silver, there's some technical reasons, well, not technical reasons, there are reasons why, which we'll get to in a minute. But basically, well, I'll tell you right now, the idea is that a silver atom, its atomic structure, as we understand it now after quantum mechanics, has a special relationship with the electron shells. And it turns out that there is one valence electron for the silver atom. So it turns out that the entire kind of angular momentum representation of the silver atom is due to that valence electron. So in essence, what you're doing is when you're measuring the angular momentum in its ground state of the atom, you're really measuring the angular momentum of that one electron. And the other reason, well, why can't you just use electrons? Well, there's a reason for that. Because what happens is once you have the oven, you make a collimated beam, and you send it in through a magnetic field that's inhomogeneous. We'll get to that in a moment why. And you want to see how it moves and bends due to the magnetic field. Now, there's a reason here, which we'll get to in the details in the next slide. But if you send electrons over here, the magnetic field will quickly accelerate and bend the path of the electron. And what the Lorentz force law tells us, that Q is equal to V cross B, it's going to quickly deviate the atom, and you won't get the results we're looking at something more subtle. So the silver atom is neutrally charged, has no charge. What we want to do is look at the interaction of the magnetic moment of really the electron, but let's just say the silver atom, with the external magnetic field. And then it will go and it'll have a photographic plate on the side, and you want to see how do they scatter or bent by the magnetic field. Okay, now for some details, we'll go to the next slide and we'll get into this a little bit deeper. So when we talk about particles, and again, we're going to interchange the silver atom with the electron. So if I say electron or I say silver atom, they essentially mean the same thing in this story. But I'll just say it, the electron has a magnetic moment mu, and it's a vector that points. And again, this should be familiar from our AP physics class. And within a magnetic field, we know that the energy, or the potential energy, of that magnetic dipole in an external magnetic field is minus mu dot B. Again, it wants to align with the field that lowers the potential energy. Now, if there is a potential energy, then the force on the particle is just going to be nabla times the energy, negative of the gradient of the energy, remember? And in this case, it's simply the gradient of mu dot b. So that's how we find it. Remember, that's just going back. Remember, it's just F is equal to minus, derivative of potential energy with respect to position. That's essentially what we're doing here. Now, in the Stern-Gerlach experiment, remember we said that the field was inhomogeneous, and in that case, what we will show, is that the field is essentially linear in that it gets stronger as you go up. As z increases, the magnetic field increases. And if you do recall, and I'll show the image again in a moment, the B field is actually pointing down, but the gradient is what's important here, is increasing upwards. And the silver atom is electrically neutral, so there is no Lorentz force law involved here. So again, as z increases, as we go up, we'll define z as upwards in that image. The magnitude of the B field grows. But then all we need to do is plug this in, and we'll simplify this. That, well, again, since we're taking a dot product, and we're only going to have a change in the z direction. So this gradient simplifies to partial z, mu z, bz, where mu z is the z component of the magnetic moment, and bz is the z component of the magnetic field. And when we take that, the magnetic moment in the z direction is constant with respect to z, and we get it's proportional to partial b, partial z. Now here's the story. So again, this is measuring a kind of the angular momentum, or the magnetic moment, if you will, of the silver atom, or the electron in this case. Now this is where the story gets interesting, so let's bring back our experiment here. And now the idea is, what's going to happen to this particle as it passes through this field? And again, notice the little blue lines represent magnetic field. They're getting denser as you go up, as we said. So essentially what this is going to happen, this is going to exert a force in the vertical direction. So notice, though, that if the magnetic moment is pointing up, in this case, the interaction here is such that it's going to exert an upward force on it. If the magnetic moment is pointing down in the z direction, or has a z component downward direction, the force on it is going to be pointing down. So you're going to get a spread of these electrons hitting the photographic plate, or the silver atoms hitting the photographic plate. Now, so here's the important thing here is, classically, what do we expect? Well, think about this for a moment, that now we have these random silver atoms coming in with randomly distributed magnetic moments. That means on a three-dimensional, or two-dimensional sphere, if you will, on the 3-ball with a 2-sphere, if you will, that it's going to be equally likely for the magnetic moment to be pointing in any direction. That's what we mean. In 4 pi steradians, if you will. And so if we draw the z-axis like this, what that means is that if it's equally distributed in any direction, then we just look at the z component. Well, there's many more possibilities for the magnetic moment to be around the equator, if you will. And there's very few for it to be, say, towards the top. Again, you could just relate it to the area of the sphere if you want, but just projecting that onto the z-axis. What that means is that we'll get a distribution of the z component of the magnetic moment that looks as follows. It's going to go that. So maybe we'll make it a little bigger. So it's going to be, so most of the z component of the magnetic moment, if it's distributed randomly, are going to be right around the center. Now notice that if the magnetic moment is perpendicular to the z direction, this dot product is 0, and there is no force. So in that case, for those magnetic moments that are 0, they're going to go straight through and hit the center of the plate. Very few are going to hit the extreme ends, and we're going to get this distribution, which I showed up above, that we get this. So that's the result we expect. But of course, we're talking about classical physics. And again, these little ones go down here. The extreme cases are going to go up in there. So what was observed? Well, something that we should find surprising. Actually, it's an extremely unintuitive result. But let's see if I can get this to work. Yes, let's try to erase a little bit. The result was that they did not see that. Because, of course, we're in the quantum realm, so if it were, we would be surprised. We'd not be in a quantum mechanics course. But what they observed, they saw just two bumps. They saw one here, and they saw one here. And actually, well, yeah. Now, I'll show a picture of the actual results on the next slide. And so that's interesting, and you can think of it, well, okay, well, that seems like then there's only two cases, that they're either only pointing up or pointing down, but we know that's not the case classically. So what it says is that when we do this measurement, somehow it's picking out, or it's changing the state to be either up or down. And again, we call this spin up, if you want, and spin down. We'll get to the notation in a minute. Now, you might say, okay, well, they're either pointing up or down. But however, you might say they're coming out of the oven, either pointing all up or pointing down. But all you have to do is rotate this this magnet here. If you rotate this, you always get two bump, and they just kind of rotate along with the direction of the z, or the component of the direction of the magnetic field, such as you always see two bumps orientate along with the magnetic field. So that's bizarre. And that's an extremely unexpected result, and it's purely a quantum mechanical effect that can't be explained by classical physics. But what we really care about in the end is that we have a two-state observable here. And this is called spin 1/2 for an electron, which means essentially, well, in the end, it means that there's two possibilities of outcomes. There's either it goes up or it goes down. And we'll talk about the values of these in the angular momentums in terms of h bar, and we'll return to that in a minute. Now, and we'll also talk about how you can arrange these things and do various experiments with these and combining them. That's an interesting result. And there are also other cases. We have objects with different angular momentums. So not spin 1/2, but spin 1, you'd have 3 bumps, and so on. And then spin 3/2, you'd have 4 bumps, and so on. But we're going to concentrate on spin 1/2 because we just want to talk about two-state observables. Now let's look at the actual result, or at least the first result. Here it is. It was a postcard sent to Niels Bohr from Stern and Gerlach. And in this, this side here is when the field's turned off. And again, so the direction of the magnetic field goes in this direction. And then they turn the field on, you get this kind of looks like a lipstick or something on here. But actually, it's this separation here that is the interesting part. And so, again, the field is weaker here on the edges. So it's really the central part. And this is a very famous picture showing that you get this splitting, that they only hit at the extreme edges. Now, nowadays, this is seen as a measurement of the spin 1/2 electron through the angular momentum of the, because the angular momentum of the silver atom is 0. But at the time, it was interpreted incorrectly, and later it was corrected. But let's take a little bit. Let's take a look at this and see how we want to represent it in quantum mechanics. This is what we really care about going forward. So there's two possible outcomes, and if we go through the full mathematics, which we did not do here, we would actually find that the actual value of the angular momentum is either plus h bar over 2 or minus h bar over 2, and that's why it's called spin 1/2, because it's h bar over 2. And there's only two outcomes, we call this. Now, there are different representations for this. Sometimes, like I've said, it's called spin up, spin down. Sometimes called plus or minus, or just an arrow up or arrow down. In Susskind's book, he calls it U and D for up and down. But the interesting thing here is we want to see how we represent it. And again, in the previous lecture, we said how we do that. We do it with our two-dimensional Hilbert space because we have two outcomes. Now, the basis kets here can be spanned by the two outcomes. And I've used this notation here. It might be changing, but again, you just need to know that there's a two-dimensional Hilbert space. And here I put a subscript z, saying that the spin is up in the z direction, spins down the z direction. That's what we just had. But we'll see that actually you can label them differently. And actually the result is direction dependent. Like I said, if you rotate the magnet, those two dots will go along with the magnetic field. So we can label them in different ways, but in a convention is to choose the z direction as your basis and write everything else in terms of those z's. This will make more sense once we kind of elaborate on the relationship here. So we'll just call the up ket the up in the z direction and down the z direction. But we can also rotate the x direction, perpendicular to the z direction, or the y direction. So we'll have various kets that we can represent it. But remember, we're all talking about the same two-dimensional Hilbert space. It's just that we're looking at the result in different directions. And again, any direction will give, so there actually is a continuum of directions, if you will, but it's always the same two-dimensional space. This is like rotating a basis in the two-dimensional plane, essentially. But we'll see it gets a little more involved because we're dealing with complex vectors. So it's a complex vector space. And later, we'll go through and relate these ket vectors. How do you express x in terms of z and y in terms of z and so on? But again, the point is they all reside within the same Hilbert space. It's just that there are different bases within it, if you will. And we'll come back. And then we'll need to elaborate a little bit on the mathematics here of the kets, etc. But this is essentially our kind of stomping ground is this two-dimensional Hilbert space. There are other physical representations, which we'll talk about later. One is the polarization of photons. It has two outcomes. That's one we'll probably concentrate on as well. So there'll be two physical systems we'll definitely concentrate on.